Welcome back to the fourth lecture of this mini course. So far we've talked about three different models: the GNP model, the model of random graphs with a given prescribed degree sequence, and about random geometric graphs. We've talked about connectivity in all those models, and we've proved the existence or the threshold of a giant component for Ehlers-Danlos random graphs. So now we're still I'll still show something for graphs with a given degree sequence, where the degree sequence is a bit more unbalanced, in the sense perhaps more realistic for certain networks, where the configuration model in principle does not work. Okay? So we're back with random graphs with given degree sequence. That's the last non-geometric part of this mini course. Afterwards, what's remaining will be some sort of percolation and some general so-called kernel-based random geometric graphs. But we focus here on random graphs with a given degree sequence which are relatively dense, where the configuration model does not work. So in particular, if you remember that, for example, if we were doing the configuration model and we have here a vertex V with a high degree, then we cannot hope that the probability of obtaining a simple graph is bounded away from 0. There might be setups like the connectivity setup yesterday, where we can prove higher concentration for the error probability of being connected in this model, and we can maybe still find a way out. But in general, if the graphs are too dense, then this does not work. So let's assume that we have a model where the configuration model just does not work, but we can still do some things in such a model. As I said, we cannot in principle hope for some sort of monotonicity results, in the sense that if we have, for example, a fixed number of balls in each vertex, and then we just add something to one vertex, for example, we cannot hope in principle for monotonicity results, like saying that, okay, if we add balls, then we make the graph more connected, because those balls, they change the distribution of everything. It's not obvious how to construct such a coupling. But for those dense models, one idea that one can use a lot, one idea for dense models, and we'll go in that, we'll explain that in more details, is the so-called switching method. So what is the basic idea of switching in a graph with a given degree sequence? Well, the idea is that we are given a graph with a given degree sequence, and we produce another graph with exactly the same degree sequence, meaning that for every vertex the degree is the same, and we do just some local operation. So what's the simplest switching you can think of? Well, imagine the following. You have 4 vertices, A, B, C, and D. And imagine between those 4 vertices, we only have those 2 edges, namely only the edge AB and only the edge CD. Every vertex has degree 1 in this setup. And we can do a switching in a sense that we take out some edges and we put back in other edges in such a way that the degree sequence remains the same. Right? So you can imagine you can do it, for example, in this way. So you take out those edges and you put in these 2 edges. Then it's still true that every vertex has degree 1. It could also have, instead of the red one, I could also have done this, right? Could also have done the blue stuff. Right. These are 2 possible switchings from the original setup, always assuming that these were really non-edges. So what I'm not drawing here, these were not edges. So AC and AD were not there, BC and BD were not there. And then we can either get the red graph or the blue graph. And in both cases, the degree distribution is the same. Right? So it's a sort of double counting idea in the sense that whenever you start with some bad graphs, for example, these ones that might not be connected, you perhaps can do some switchings to construct other graphs that will be connected. And if you construct many more graphs, then the probability to get a non-connected graph is small. The only issue that you have to take into account is, of course, if I'm starting with different graphs, I might end up with the same graph after having done my switching. So you have different ways from here to construct a new graph, but it might also happen that there are different graphs here that give you the same graph after switching. So you kind of have to you have to bound. First of all, you have to say that at least as many graphs you can construct from those bad ones, but also there are not too many ways to obtain the very same graph here, so that even when counting these multiplicities, you still get that those bad graphs are much less than those good graphs. Okay, so let's try to formalize this a bit. So switching allows for comparing sizes of subsets of graphs, for comparing sizes of E and F, which are subsets of graphs with the same degree sequence. And you can imagine the following auxiliary graph. You have here your set of E. These are graphs. Think about these as bad graphs. And here you have other graphs, F. Think about these as good graphs. And there are some graphs in here. Every vertex here, so make an auxiliary graph. Every vertex here is a graph. So this is my graph. There's one graph G that belongs to this family of bad graphs. So I have one bad graph. And in here I have, say, my good graphs. And then, let's say here I take one particular one, G prime. And I say I put an edge between two graphs if I can obtain G prime by switching from G. Okay? So I say in this auxiliary graph, I put an edge between G and G prime. If there is a single switching, namely just a pair of edges that I take out and I put it in either in that way or in that way, such that G prime is obtained from G. Okay, that's my auxiliary graph here. Okay. And now imagine the following situation. Imagine that for each vertex in E, suppose these sets are disjoint, suppose you have at least a degree of, let's call it dE minus, meaning that from each graph here, you can construct at least dE minus many graphs in here. And for each graph in here, there are at most dF plus edges coming in, meaning that every graph can be obtained by at most dF plus graphs that are from there. Well, then by just counting, by double counting the edges in this auxiliary graph, what do we get? Well, the number of edges in this auxiliary graph well, it's just double counting, right? So it's on the one hand, you know that the edges are at most dF, I counted from here, so it's at most dF plus times the cardinality of F. But it's at least dE minus times the cardinality of E. Okay? And since we think about picking one graph at random, one graph uniformly at random from all graphs satisfying this given degree sequence here, we might think of this as an event, right? So we might think of E to be the event to pick one graph here, and F to be the event of picking one graph here. So just with the uniform sampling, we assign probabilities here. By sort of abuse of notation, we might see these as events, and then get that the probability of this event here, namely to choose this one, is at most this number here. Meaning that if we can show that this factor here is such that, if, for example, if we show that this factor here is little of 1, say this factor is tending to 0, then it means that the set of graphs here that are sort of bad is little 1 times the other graphs here. Meaning the probability to choose a bad graph, therefore, is small. Okay? That's the main idea. And we'll apply this idea for showing the existence of a giant component where, in principle, the configuration model does not work. Any comment? No. Just call it double counting or call it switching. It's very similar. Okay. So the one theorem that one can use, for example, if you have a given degree sequence such that the sum of the degrees of all vertices is at least n log n, and the degree of each vertex is at least 1, then asymptotically, almost surely, G has a giant, not just a giant that is constant times n, but it's a giant that contains almost all vertices. Okay. So this is in principle when you have these degrees, the configuration model does not give you a constant probability for obtaining a simple graph. Well, the the question is then how to define those bad sets E and F. Well, it will be those will be bad where the graphs will be bad where each component is too small. So let's fix some k, which is even tending to 1 times n, but we can put here, for example, 1 over root log n. So this can be made precise, but I'm not aiming for this. And we kind of have to split the bad graphs. That's usually what has to be done, to kind of split your probability space according to some quantity that allows for nice counting. And the good trick here is that for each k, for example, let me call it fk, be the event that the graph has exactly k connected components of G having exactly k components. There's a subset of graphs where we have exactly k components. And fk prime, I switched somehow from E and F to fk and fk prime they will be the bad ones are those that exactly k components, graphs with exactly k components, and each component at most of this size, capital K here, and each size is at most k. So I switched a bit notation here. So these are all my graphs sort of sliced up into those having a certain number of components, and these are subsets of the graphs, namely those that have k components, or that not only have k components, but also have each component bounded by this capital K. And then we say f prime is just the union of those bad ones, fk prime, summed over all k. Well, since the case when there is just one component that's definitely good, so we start the union with 2. And the goal to show is that the probability that f prime happens tends to 0. Or let's call it little of 1 here. So what's the purpose of slicing up the probability space into those disjoint fk prime? Well, it turns out to be easier to just increase or decrease the components by 1. So in particular, it suffices to show that if we have this, that for all k, the probability of this fk plus 1 prime let me write it as is smaller or equal than f of n times the probability of fk, where f of n tends to 0. Because if we show this, indeed, so let me just say why this is enough. So indeed, if we show this, then the probability of f prime, which is just the sum of those fk plus 1 prime, starting with 1 now, okay, and this is 1 here. So the probability of having a bad graph, f prime, a graph where each component is of size at most capital K, tends to 0, right? That's the idea of slicing up. So this is usually the non-trivial part when you apply switching, that you have to find a good way how to split your how to partition your probability space. Perhaps it might not work in the first way. Your first idea how to split it, perhaps it does not work, but if you find the right way to split, then this is relatively easy. And here it's kind of natural to say, okay, since we want one component that is big, well, what can happen after switching? Well, you can get one more component, or you can get one less component. So it's kind of natural to split in such a way that you start with a graph having k components, and then you do some operation which might increase or decrease your number of components. So, okay. So we need to show then, so set just for, if you want to do the calculation, I will not. For example, fn tending to 0 could be something like this, say 16 root log n. And we want to find, we need to find s plus and s minus in the same way as this d minus d plus, such that the probability of fk plus 1 prime is less than sk plus over s plus, not depending on k, s plus, s minus times the probability of fk with this smaller or equal than f of n. And s plus and s minus have exactly those meanings as here, so I write it maybe quickly again, where s plus is such that at most s plus switchings end up in a graph, in a fixed graph in fk. So we need to bound that this one is not too often appearing as the image of some graph here. And also S minus is such that at least S minus switchings go out of a fixed graph in fk plus 1 prime. Okay, so that's then we exactly that in that setup here, right? So we need to bound the number of, if you want to say the number of repetitions. So you can think about, if you think about in terms of double counting, or in terminology of double counting, you can construct many graphs, and each graph should not be repeated too often. So the number of constructions should be large, and the number of repetitions should be small. Okay. So how do we do that? Well, it's not so difficult. So take a graph H in fk plus 1 prime. And if we want to end up in fk, well, then we need to merge two components. If we want to end up, so we need to merge two components. to end up in Fk. So what do we have to do? Okay, suppose we have a component here, C1. There is one edge here between U and V. We somehow should merge this with another component, C2, where we have another edge, maybe, U prime and V prime. Okay, how can we merge these two components? Well, we have to make sure that this is not a cut edge, meaning an edge that disconnects. Because imagine the component were like this. If I do some switching now, and imagine like this, imagine that these are cut edges. Well, if I take those out, those edges, and switch and make it like this, right? Then without those two edges, I still have two components. That should not happen, right? So I better avoid the fact. I better avoid a cut edge or a bridge in that graph here, right? So if I have UV such that UV is not a cut edge, UV is not a cut edge. Okay, so this edge is there, but it's not disconnecting this component, so the component stays together. And the other component, I don't care about that. Maybe this is even a cut edge. I don't mind. But if I have two components, C1 and C2, and I do, for example, the switching to the blue ones, meaning that I take out this red one here and this yellow one here, then you can see I merged the components, right? Because that's now one component. Okay? So it does not, so if I fix UV, one edge that is not a cut edge, then I'm fine, then I don't care what the second edge is. Okay? So UV should not be cut edge. And U prime, V prime, any other edge in another component, no matter whether it's cut edge or not. So we just have to take one non-cut edge in one component and any other edge in another component. And we have to count how many choices we have. Okay, choices. Okay. How many choices? Well, a cut edge is an edge that appears in all the spanning trees of a component. Because if a cut edge is not in a spanning tree, well, then I can take it out, and there's still a spanning tree of that component, and the component remains connected. So the cut edge has to be in all spanning trees. But by assumption, we said, okay, I erased this. We said that it was written here that the sum of the degrees is at least n log n. But a spanning tree has n minus 1 edges. And even if we take into account that for each pair of edges there are two choices, namely the blue one or the cross here, well, the number of cut edges is therefore at most 2 times n minus 1. And therefore, the number of non-cut edges is at least n log n minus 2. Minus 2n minus 1, okay. And for the second edge, well, since we are starting in a graph in Fk plus 1 prime, it means that every component has size at most k. by assumption of this prime here, each component has size at most k. And moreover, the degree of each vertex by assumption was at least 1. We said that there's at least one incident vertex, one incident edge to each vertex. So the number of choices for the second edge is therefore everything except for those that are already in the first component. So the first component has size at most k. So there are at least n minus k vertices outside, and therefore n minus k edges. So the number of choices, therefore, is at least n minus k. So therefore, combining this, S minus is at least this n times log n minus 2 times n minus k. And by choice of k, this is at least n squared root log n over 2. Okay, so then we get a lower bound on S prime. So S prime is not too small. Similarly, we have to do an upper bound on S plus. So for S plus, we have the following claim. The number of pairs of oriented edges uv and xy such that by switching those edges, one has one more component, That's now for the opposite direction, because we want to get a bound on S plus, so such that by switching those edges, one has one more component is at most 8n squared. Okay. So if we show this, so I didn't show this yet, but if we show this such that the number of pairs of oriented edges, or which correspond to these two choices of changing one cycle in two different ways, well, if we show this, well, then once the claim is shown, well, then S plus is at most 8n squared, and then you see that we're done, right? Because we get that S minus divided by S plus is less or equal than this 1 over root, or 16 over root log n, and we're done. Yeah. Using this bound and this bound.
It's the opposite. S plus divided by S.
Yes, you're right. Yes.
I have a question. Could you repeat how you get the lower bound of the number of non-cut edges?
Here? Yeah. Okay, so we said by assumption the total sum of degrees was n log n. And if you think about edges in an oriented way, meaning that when you have a choice, then you can do either the blue one or the cross. So that gives you this extra factor 2, so that the degrees is equal to the total number of oriented edges. So you get at least n log n oriented edges in total. But you should not take a cut edge. And the cut edge is an edge that is present in any spanning tree. A spanning tree has n minus 1 edges, 2 times n minus 1 oriented edges. So I have to take at most those out. So I get at least n log n minus 2 times n minus 1. And I put just minus 2n here. Okay. Yeah, this claim is not so hard to show. So for the claim, proof of claim, it remains just to show this claim. Okay, the first observation is that uv and xy have to be in the same component. The same component. Well, because if not, imagine that u and v and x and y are in different components. Well, if I'm switching those out, I'm calling it switching out, and switching those in, yeah, the number of components does not increase, right? If not, number of components does not increase. Because we had 2 components before and we had 2 components afterwards. Or even, it might be even 1 if this edge is, if one of those edges is also there. But they have to be in the same component. That's the first thing. And then there's just 2 cases, either say uv, one of them, say uv is a cut edge. Is a cut edge. Well, then the other one has to be as well. So let's suppose here is xy. And here is the edge uv that is a cut edge. But xy, imagine, is not. For example, we have these edges. If uv is a cut edge, let's put it this way, but xy is not a cut edge, imagine we have this situation here. So then when I do the switching, say, for example, adding this edge here, that's my new edge, and then this one here, and I take this one out and this one out, well, then I did not increase the number of components. Yeah? So if xy is not a cut edge, if xy is not cut edge, we don't disconnect. We do not disconnect. So, right, if uv is a cut edge, and the picture says if xy were not a cut edge, then after switching we would not disconnect. So xy has to be a cut edge as well. So both are cut edges. Both uv, xy are cut edges, meaning they have to be in a spanning tree. Okay, there's 2 times n minus 1 choices here and 2 times n minus 1 choices here. So at most 4 times n minus 1 squared choices here. Okay. And case 2 is similar, that none of them is a cut edge now. Case 2, none is a cut edge. And yeah, I will not, in a similar reasoning, I will, in a similar way, you can also show there are at most 8n squared choices. I will skip this part a bit here because it's a bit more of the same. Again, an analysis, okay? And this gives you this claim, and this gives you the desired result, okay? So this is this part of the lecture. Okay. Any comment on this? No. Okay, I think this is a relatively easy tool. I think quite combinatorial and relatively intuitive. The only hard thing or the only non-trivial thing here is, I think, how to find the splitting, but it's also not so difficult. Okay. So now I want to switch topics and, as I mentioned before, go to geometric setups. And I first want to show a concentration inequality which is not so well known, especially for people working in random graphs, because it comes from a different area, but it has very nice applications for different geometric models. And the concentration result we have, I want to mention, is the so-called OSSS inequality. Named after O'Donnell, Sachs, Odeh-Schramm, and Rocco-Cervedio, which in principle has nothing to do with random graphs, but we will see how to apply it. So what's the setup? The setup is the following. So consider a Boolean function there is a vector of zeros and ones of length n giving either 0 or 1 and the only thing you're allowed to do is to ask queries. So what is my ith bit of my value of this function until this number is determined, right? So you get a vector of zeros and ones. You can query, tell me what's the ith entry, and you're allowed to ask these questions until it's sure that, or it's clear that for this particular function you get either 0 or you get 1. At that point you stop your algorithm. And then, so let's say we have an algorithm that can be randomized and will be randomized, and an algorithm typically randomized that reveals the coordinates one by one, but you can choose the order, revealing the coordinates one by one until the value of f with this random input, let's call it w for random 0, 1 n vector, say, is determined. Okay, so imagine you don't know much about the function. It will depend on n coordinates, but you can successively obtain information. Okay, tell me what's the ith coordinate of the input. Is it a 0 or is it a 1? Okay, then according to the information of the ith coordinate, maybe ask the jth coordinate and so on, until you say, okay, now I know the function will evaluate to 0, or until evaluate to 1. And the goal in this setup is kind of to reveal as little information as possible, only few bits, until we know the answer. So the idea is kind of reveal as little as possible. Okay. So then for a bit of notation, for an n tuple x1 up to xn, and t less than n, let's write x1, write x subindex t to be x1 up to xt, and w with index I sub t will be the values of the configuration w at those bits at x1 and xt. Okay, so I'm just telling you kind of these are the positions x1 and xt. These are the positions x1, xt that I will be querying, and these are my values that I get. W at so w is a vector in 0, 1, n here. So maybe I should have said that. I'm telling you these are positions x1 up to xt that I'm querying, and this is my value at position x1 and the value at position xt. And then just what is an algorithm in this setup? An algorithm T is something that depends on a deterministic starting bit, I1, starting bit, deterministic, and the function, an evaluation function, psi of t, that tells you which bit to take for t smaller than n, that takes w in 0, 1, n as input, and gives an ordered sequence and gives back an ordered sequence of bits to be queried, and gives back an ordered sequence of bits that sequence of bits, well, I1 is determined, I2 up to In, that are constructed as follows. Okay, so for t bit, I1 is the bit, the first bit is deterministic, but for the second and so on and until the nth one, this IT, well, is this evaluation function at the t steps applied with the information I had from before. So all my t minus 1 bits, this is this notation here, that we had chosen t minus 1 bits before, and with the information of the values I had obtained. And I should find a bit, well, typically it's stupid to reveal a bit that I already had revealed. So I'm choosing a bit. This evaluation function will give me a bit among my n bits that I haven't revealed yet, right? So it will be something except for the t minus 1 already revealed. Okay, so this is kind of, think about it as a decision rule, right? So you have already this information with these bits were the ones that we had queried at time t. This is a decision rule saying these were until t minus 1 we had those bits revealed, giving me these values, and I should find now a new bit that should be different from those t minus 1s so far, in the hope that I quickly obtain the value of the function. So that's my sort of stopping time, so not stopping time in the sense of a martingale, but stopping time of the algorithm, define tau of a configuration that depends, of course, on the function and the algorithm for this given configuration is then the minimum t, where I know the value of my function, so that for any x in 0, 1, n that coincides on the first t bits gives the same value under f. Okay, so such that x on these t first bits chosen, if that equals to w on all those t bits chosen, well, then fx is equal to f of w. That's the point where I stop my algorithm. So the notation is maybe a bit confusing, but the idea is very simple. If I have enough information by the first t bits, the ones that I picked, namely I1 up to IT, which are all these positions, and if I find a vector x such that on all these t bits the value of x is the same as the value of w, then we must have that the function evaluates to the same value, namely in both cases 0 or in both cases 1. So if that happens, then I stop my algorithm because I completely determine my function f. Okay, so it's for those of you who know Talleyrand's inequality, it's perhaps a bit similar in the sense that you want a certificate for already a certain value. If not, forget this comment. And okay, that's the setup. And what's this inequality now? Well, imagine now that each entry of w, that each entry of each coordinate of the 0, 1 vector w is 1 with probability p and 0 with probability 1 minus p independently of each other. And then the OSS inequality says the following. If you take any constant p between 0 and 1, any n, and f to be an increasing function, Boolean function, so far I hadn't put any restriction on f because you can define all this, but it's kind of natural to impose some condition because otherwise it can happen that you have to go to the very end, because if you don't impose anything, it could be just that no matter what you do, the last bit will flip your result of your function f. So now let's assume that f is increasing, meaning that if I flip one extra bit from 0 to 1, and f was already 1 before, then it still is 1 afterwards. Yeah, so it's like in the same sense as we had for Erdős-Rényi random graph. If I have a graph and I'm adding edges and the graph is already connected before, and after switching my bit, I will still be connected. Here is the same. So I have some increasing function, meaning that if I switch one entry of the one coordinate here from 0 to 1, and if before that switching the function value was already 1, it will be 1 afterwards as well. Yeah, that's what increasing means. Yeah, so it's increasing in the arguments. And consider an algorithm T, an algorithm in that sense, T, well then, the OSS inequality says that the variance of f for a fixed p so you can think of f maybe being for example, a Bernoulli, right, that takes 1 with a certain probability and 0 with another probability. So the variance of f in that case would be just the probability that it's 1 times the probability it's 0. But it could be more general. But keep this in mind. Maybe that's if f, for example, is 1 with probability q, say in total, then okay, this could be q times 1 minus q. But the OSS inequality says that the variance of f is then bounded by p times 1 minus p times the sum from 1 up to n of a product of two quantities which are called delta IT, which I'll explain in a second, times the probability that the bit I is pivotal for f. So let me explain this. That's the inequality. Okay, what does this mean? The probability that the bit I is pivotal for f. A pivotal element means that this is really important. This element is really the one that changes the value of the function. And since we have increasing functions, it means that whenever this bit, when this bit is 0, then the function evaluates to 0. And when this bit is 1, the function evaluates to 1. So you can also, if you prefer this as the influence of bit I. Okay? So this means that swapping this particular bit is really crucial. Yeah, so there's sometimes in those threshold events, it happens that there is one single edge which makes the graph connected or not connected, or there's one edge which makes a giant component or an infinite component. And this means that the ith bit, or the ith coordinate, you can think of this n here is the number of edges. So there's each entry here could be, for example, associated with one edge, and one particular element is pivotal. Okay? And delta I of t, well, it depends on f, is the probability that the ith bit is revealed. Is the probability that there exists a t smaller than the stopping time of this algorithm here, such that the bit chosen at time t was I. That I t is equal to I. Okay, so that's the probability that the ith bit was revealed by the algorithm. Okay, so probability that ith bit revealed. Okay, so that's the setup. Okay, it's not immediately clear how to apply this. This comes from communication complexity. But what's the idea? Well, the idea is, for example, that if you have a random graph model, and I'll explain that in the using percolation. then imagine that each entry here corresponds to having an edge or not having an edge. 0 is not having the edge associated with that index, and 1 is the event of having the edge. And then it means that the variance of f, meaning the kind of the threshold width, in other words, so if you have your f here, f will be increasing. It could be increasing this way, or it could be increasing even sharper, or it could be increasing much slower. So the variance of this somehow tells you something about the threshold width. And if you want to show that f has a sharp threshold in the sense that it's 0 and then just a few bits will make it 1, well then we want to have a bound here such that this is small here. So we want to find an algorithm which is such that for each bit here, the probability that the ith bit is revealed by this algorithm is small, right? And then this part will be small. And also the probability that the ith bit has influence should also be rather small. So this is something that is usually harder to get. But what you can get here usually is to find an algorithm such that this revealment here is low. Because then when you have this, maybe you know the variance of f, if f is a Boolean function, then you can get a lower bound for the probability that a bit is pivotal, and if you get a lower bound for a probability that a bit is pivotal, well, what does that mean? That means there's a quite good chance that just those few bits change your value from 0 to 1, right? So you think about it maybe in a geometric setup. That's perhaps the easiest way. If you're looking at the grid, that's what we are. Close to the threshold, whether for having a giant component or not. Imagine, well, we're doing bond percolation. So we're looking at Z2. The vertices are Z2. Let's say we have an infinite graph, but then we can finitize it later and restrict to a finite box. Okay, so let me be more formal here. Let's do bond percolation, meaning the graph is such that the vertex set is Z2, just the grid, and each edge is open with probability P. Okay, so independently. So you have some edges open. Here is 0, the origin. Some edges are open. And what you're typically interested in, one event or one particular instantiation of this function f, is the probability whether 0 is connected to the boundary of the box of size n. So imagine this is this Z2 restricted to an n by n box. So this is n here, let's say. This is n here as well. This is 0, and this as well. Okay, and imagine we have on the boundary also points, so these ones. Okay. Of course, the Z2 goes on here as well, but I'm not caring about this. I'm caring about the event whether 0 or 0 is connected to some point on the boundary. So for example, I can, for one particular choice of f, I choose my, let's define theta n, depending on p, to be the event that 0 is connected to the boundary of the n by n box. Let's say the probability that the origin is connected in bond percolation to the boundary, to delta lambda n. So this is lambda n here, the whole box around it, and to the boundary by a path of open edges. You can see that, okay, this will depend on p, and the more edges in red I have, the easier it is to connect to the boundary, right? So this is one particular choice for this function f here, because this f is increasing, it gives you 0 or 1. So here you can see exactly what this f is, namely, okay, I should reveal as many edges as needed until I'm sure to say that 0, 0 is connected to the boundary or is not connected to the boundary. Right? So, for example, in this case so far, I don't have a connection to the boundary. Okay, but imagine I have these edges there. And if I know my function f, and I know that this edge is there, so here I put my, so let's say this was my 0, 0, and I'm querying a certain number of bits. So for example, I'm querying this bit, I'm querying this bit, this one, this one, this one, and this one. Then I know already that my function f to be connected to the boundary will evaluate to 1. Right? So then I can say at this point I stop my algorithm because I have an increasing event. I don't care anymore what are the other edges, because if it's already connected, then I have already my connection to the boundary. And I should try to do it in such a way that maybe not too many edges are explored at the same time, right? So I mean, of course, I don't know before checking whether or not these edges are there or not. Similarly, for example, if I knew, for example, that this edge was not there, and this edge is not there, and this edge is not there, and this edge is not there, then I can also stop my algorithm, right? So, because for example, if I knew that this was not there, this was not there, this was not there, and this was not there, then I know that this point is isolated and it will not connect to the boundary, and I can also stop my algorithm. Of course, I also, perhaps one could think, okay, I'll do a classical breadth-first search in the sense that, okay, I will first check all these edges, and if some of them are there, then I go from there to the neighbors of this. But if I do that, then I'm doing something which is suboptimal in the sense that for sure I will check these edges. So these edges here, they have a very high revealment probability. And that's not good, because if I'm doing this, then for these edges here, I get a high revealment probability, and this revealment probability will tell me something, okay, the variance is maybe relatively large, and I cannot hope for proving a sharp threshold from 0 to 1. In a similar way, if I start, for example, always at a fixed position, this one, say, and I try to go from here, the same thing will happen in the sense that those edges will be revealed for sure, and I get a high revealment probability for these, and that will not be good for that upper bound there as well. So the idea then, well, that was an idea due to which I will prove next week, due to Hugo Duminil-Copin and Vincent Tassion, is to consider a randomized algorithm that keeps the revealment of all edges low, keeps probability of revealment of all edges low. So just in 1 minute, the idea, what does the algorithm do? I'll explain that in a bit more detail on Monday. Well, the idea is the following. If you have here your origin, and here you have your boundary of the n by n square, well, as I said, it would be bad if we start the classical breadth first search from this point. It would be bad to start here and do, say, breadth first search here as well. So what does Duminil-Copin and Tassion do? Well, they say do the following. Take a random distance from the origin, say k, say lambda k, and start exploring from the boundary of this lambda k towards the inside and towards the outside until you know whether or not you have a path here. Because the observation is, okay, if there is a path from 0 somewhere here, it has to cross somewhere this k. So if I'm starting at a random number k, say here, and I know, for example, that for all those points that I started here, I cannot continue anymore because I don't find further edges. Something like this, for example. If I end up in a situation like this, then I know already that there cannot be such a path, because the path would have to go through these blue edges, but 0 is kind of blocked, right? 0 cannot exit here. And in the same way, if it were the opposite, it could be that from there, exploring both sides towards the inside and towards the outside, if we find a path, something like this, for example, then we can also stop, right? Because then we know already that the path exists because there is a connection from 0 to the origin. But the advantage of doing this is that since you kind of randomize or average, if you want, over all those kind of k where you start, no particular edge has a high revealment, and then this number here, this delta I, is small. Since here we have a Boolean function, namely you're either connected or you're not connected. It's just if q is the probability of being connected, and you have here for the variance q times 1 minus q, you get a lower bound for the probability of a bit of any bit being pivotal. And that, using Russo's formula, then tells you that you will have a sharp threshold, and meaning that the fact of having a giant component will jump from 0 to 1 relatively quickly. That's the idea that I will explain in a bit more detail on Monday. Okay. Any questions? Comments?
So how does this apply to the random graph inside of the?
Yes. So I didn't say this yet. But okay, this is a general setup which we can use for showing the existence of a giant component, or for the existence of a path from 0, 0 to n in the standard percolation model, right? But you can do it not just for a standard percolation model, but also, for example, for random geometric graphs, because you can think about it in this way. Okay, if these are not just edges, but rather points, well, you can say, okay, you start with your point somewhere here, for example, and then you try to go inside and outside, inside and outside, inside and outside, to see whether or not 0, 0, which you can by say palm theory just artificially add, is connected to the boundary or not. So this what was done here for Boolean percolation works in a much more general setup. So I mean, this was known before the work of Dominique Copain-Tassion, using Menšikov's and other proofs. But the advantage of this randomized algorithm is that it precisely works for other setups where you have, for example, some dependencies as well. For other setups such that, like, if you know Voronoi percolation, for example, or if you know Boolean percolation, there might be some dependencies, and that's usually the hardest part, because you cannot say that one area is completely independent of another area, because you might have already explored some part. But the advantage of this is if you kind of bound the influence of each variable, then you can still apply the very same tool in a different setup. For example, Boolean percolation, for example, Voronoi percolation, and other random geometric graph models.
So there, when you are talking about the probability of a bit being pivotal for f, I guess.
Revealed, yeah.
No. The
Pivotal here?
Yeah, that one. I guess you're assuming a probability distribution on the string 0, 1 to the n, yeah?
Yeah, well, we said here that we say at each.
Okay.
More questions?